to you can use symbolic variables in MATLAB. So you say X is just X and that's it.
Good. Yeah, that's like mathematics.
And so I'm trying to use that, but now I'm running into a little bit more complications that way. But I have it commented out of how I used to run it, so it still has like the forward and back scattering, and then how I have it now.
Yeah.
I email it to myself, but if I can't get internet, then I might have to email it to you and then pull it on your computer. I don't know why it says that. It says it can't connect to Edge room.
There are a few options here to set in EduROM. A little different from the typical Wi-Fi.
Oh, okay, so now it says network authentication failed. But it doesn't mean it wants to sign in anymore.
Let's try after the class maybe. Yeah. Okay. Hello, Curtis.
Hello.
So on Friday, we had a class, but we started very late. It was my fault. I got late. And I noticed that you came and left, I suppose, correct?
Oh, yeah. I watched it already.
Okay, good. Yeah, so I just wanted to let you know that we did have a class, and my apologies for that, getting late. Okay. So we have homework 11. And you have midterm 3 on Friday. So the homework that is due on Wednesday, it is very closely related to what we are going to do in the class today. So we are going to be doing it for 1 plate. You have to do it for 2 plates. So that's all. So just to review, so today you're going to be dealing with Green's function. But let me just motivate a little. We showed that the electric potential, in the case when you have a planar conductor, or in general, the electric potential satisfies the following equation. This is the polarized, if you want dielectric function, it depends on the material. This is your electric field, correct? Epsilon times electric field, and electric field is gradient of phi, so I have written everything in one single equation. we would like to do the following example. So we did an example, which is involving the method of images, where we set epsilon of r is equal to infinity for z less than 0 and is equal to vacuum. It's a perfect conductor for the whole space, and z is less than 0 and it is equal to vacuum if it is greater than 0. And the charge density, that's a single charge. It is q, which is placed at x equal to 0, y equal to 0.
Through this 30-minute vinyasa
Sorry.
flow.
Sorry.
I thought it was Curtis speaking. Okay. So that's z minus a. So the idea is that we have a conductor, a grounded conductor, like a conductor that is grounded. That means electric potential is 0. So phi is equal to 0 inside, and you have vacuum. So this is epsilon equal to epsilon naught, and there is a positive charge you keep in front of this. So there's a whole, like a perfect conductor behaves like a mirror. That's a typical statement you make. And we argued that, oh, this is equivalent to having an image charge inside, and we would like to see that more explicitly as a solution of a differential equation. That's a description. So this is the property of the material. That's a perfect conductor. So it is infinity, and this is 1 if you want, or epsilon naught in our units. And that there's a positive charge that is placed at z equal to a. So that's your a, and this is along the z-axis. That means x is equal to 0, y is equal to 0. That's our problem. And we said for this case, we should Fourier transform this. That's a convenient way of working for it. So remove the xy components and the z component. Right? This is xy and that's z. Separate them out, and they are called the Fourier modes now. So the Fourier modes are given in terms of k power. And that's your Fourier mode, k power, comma z. So instead of looking for the electric potential everywhere, we look for its Fourier modes, so that is no xy dependence. Instead, we have k power. And for this particular case, we showed that this satisfies the differential equation minus d by dz z z plus k perp square. That's what we did last time. Equal to, you have a point charge, so it's q times delta of z minus a. That's what we, the summary of what we did last time. We are interested in the electric potential for this scenario. Electric potential is given in terms of modes, Fourier modes, and the Fourier modes satisfy a linear differential, or at this point, not linear if there is a functional dependence on this, but these are constants. Right? So that's equal to differential equation. Notice that for we are mostly interested in z greater than 0. Right? So z less than 0, there is no physics. Like it's inside a conductor, nothing. There is no electric phenomena that happens inside. Conductor is all 0. It's always outside, and when it is outside, epsilon is just epsilon naught, so it can all come out of this, either on the left or to the right, and that differential equation becomes very straightforward, and that's what we will now switch to define what is called a Green's function, which is pretty much the same equation. If this was constant, this is plus k perp square. Let me define, instead of a, me have z comma z prime. That's delta of z minus z prime. That's the equation I'll call the Green's function. If I know the solution for this, I pretty much know the solution for this in this particular case because it is a constant, right? Epsilon just comes out. I just have to put q is equal to 1, epsilon not equal to 1, and or at least redefine my equation. Okay, so how do we find solutions for a Green's function? So this is the method we want to learn, and notice what is happening here. So I have in this equation we have z greater than 0 and z prime greater than 0. So z prime is a and z is greater than 0 because we are going to be observing on this side, and z prime is the source. It is at the position of the charge. In your homework, this is not, there is not a point charge, so this is z is less than a and greater than a. This is your homework, so homework 11. In that case, z is less than a greater than 0. Z prime is less than a greater than 0. So basically, you're talking about two conductors. So there is a conductor, and there is a positive charge kept in between. So that's the scenario you're considering. It's not necessarily exactly at the center. It could be anywhere. And we are considering just one plane. So you'll notice that it's the same differential equation here to solve. It's just that the boundary conditions will be different. So what are the boundary conditions for this? Or before that, let's say, since it's a delta function on the right hand side, it has this nice feature that this is equal to 0 if z or z prime is not equal to z prime, right? Z not equal to z prime. So let me say z is greater than 0. It's less than z prime, and z prime itself is less than infinity. Right? So if z is less than z prime, this is never going to be equal. So it will be 0, right? Delta function is 0. There's also one more condition. This is z comma z prime is again equal to 0 if z prime was less than z. Right? That means our observation point is somewhere here or here. There are two different regions there. And in your homework, you will similarly say these are the two plates. There is a charge. You could be either on this region or on that region. Right? There are 2 points: z less than z prime, z greater than z prime. But your observation cannot be on that side. So in your case, it will be z less than z prime less than a greater than 0, or this could be z prime minus z less than a greater than 0. We don't have that upper limit there. That's the only difference. Otherwise, everything goes true. But we know the solution for this. Correct? What is the solution for this differential equation? We have g of z comma z prime for the two regions. If it is, this is not a harmonic oscillator, it is off by a sign, but these have solutions of exponentials. So these have solutions of exponential form. So this is a curve z plus t times e raised to minus the curve z. That's a possibility if z was less than z prime. Same thing will come out here for you. There will be two sets of solutions. But in the other region, also you have the same solution, but now the coefficients could be different because it's a different region. And how do you set this fold? How does this boundary conditions get fixed? So we have what are the conditions now? First condition is that since it's a conductor, the electric potential has to be 0 on the conductor, which means the Green's function has to be 0. So at z equal to 0, for arbitrary z prime, it doesn't matter where the charge is, this has to be 0. Why? Because it is a conductor, right? The conductor imposes that condition. The second is that electric potential all the way at infinity should be 0. So G at z tends to infinity, irrespective of where the charge is, that should be 0. So that gives us some conditions. And the same thing you will, so in your case, in your homework, what will happen is that there is no infinity, but you have conductor on both sides. So this has to be 0 at 0, and it has to be 0 when z equal to a, not z equal to infinity at z equal to a. So that's a condition that you have. Then how do you impose this condition? Put this in the solution. So this is 0. So the first solution implies that 0 left hand side is equal to, and I put z equal to 0. So I'm in this region, that means z has to be close to 0, right? So that's the first one. So that's a is equal to 0 plus b. A plus b has to be equal to 0. That means a has to be equal to, or b has to be equal to minus a immediately. At infinity, this has to be 0. That means this implies that if, so we have at infinity something has to be 0, right? This anyway is 0. So this implies that c has to be 0. C cannot exist because it goes to infinity, right? If something goes to infinity, there is no way you can go to 0. So C to begin with should be 0. So we immediately have at least found 2 of the solution. Let's rewrite that. So this is a times exponential, and b is minus a, so this is minus k power c. So that's for, and this is just d times exponential of minus k power c. Okay, that's it. But we have 2 more unknowns. How do we figure that out? So we go back and look into the differential equation. We don't need 2 more conditions. So these were boundary conditions decided by the physics, but now the differential equation itself gives some boundary conditions. So these are called continuity conditions. Let's call this continuity. Right, what we are saying is that on the left-hand side, Green's function has a solution. On the right-hand side, Green's function has a solution. And right at z equal to z prime, there is a matching conditions, which we call continuity conditions. And how do we find the continuity conditions? I integrate the first equation with respect to z. So this is minus of integral of, let's say, dz, integrate minus z comma z prime, and I do that on the right both sides. But where do I integrate from? So notice I have a line here where z is equal to 0 is here. That's where my conductor boundary is. Somewhere there is a z equal to z prime. And z itself could be anywhere. Z is a variable. This is z, if you want. So that whole line represents your axis of z. This is z equal to 0. This is z equal to z prime. And I want to integrate. So this is a point charge sitting here. I I want to integrate very close to that. So let's say this is z prime minus delta, and another point very close to the right, and that's z prime plus delta. And I want to take the limit delta tends to 0. So that delta is a positive infinitely small constant, and I want to integrate that from that. So that's z prime minus delta, z prime plus delta. And the same thing, z prime minus delta, z prime plus delta. Right. What's the right hand side equal to? The right hand side, I'm integrating from here to here.
No.
Oh, that's a delta function, so it's just 1, right? You're trying to imagine f of z here. F of z is 1. Right? If there was a delta function and integrate over z, this will be f of z prime. Right? Z gets replaced with z prime. But f of z is 1, there is no such function there. So it's just 1. Right? So the right hand side is just 1. Right? Delta function evaluates the function at that point. So you're capturing, so that's a point charge, you're just capturing that. On the left hand side, this is a total derivative. So the total derivative cancels out. So this is minus d by dz. So this is the derivative of the Green's function. Right? This is the derivative of the Green's function evaluated at z prime minus delta, z prime plus delta. Let me move this. And the second term is an integral z prime plus delta dz of g of z comma z prime is equal to 1. Notice what has happened here. This integral was of the kind dz, second derivative of dz, right? So this is what was going on. But this cancels out, right? That's a total derivative. Derivative is the opposite of an integral. So it's only this that contributes, but it's at the limits. So it's a surface term, right? It's like what happens in a conservative force, mgh. It's only the boundary that matters. So we get a condition here on the derivative, continuity of the derivative. What we're saying is that the derivative of the Green's function right on the left hand side and the continuity or the derivative of the Green's function right on the right side has to satisfy some condition. This is like derivative of Green's function is like derivative of the potential, right? Electric field has to satisfy some conditions. Remember your method of images right on the conductor, electric field always has to be perpendicular. But now there are various things that can happen. If G was continuous, so now there are various possibilities for G. Derivative is, there is a discontinuity in the derivative, but what about G itself? There's a possibility that at Z equal to Z prime, it is continuous. So this is one possibility. So this is Z, and that's your Z prime. It's continuous. It's possible that it is actually discontinuous, or it's continuous, but its derivative is not continuous. But it's also possible that this could actually be having some structure like this, or it could be infinite at that point. Right? It could have an infinite jump. There are various possibilities you can have, but it cannot be this, because if this was the case, what would be the integral of this? I'm going from right here from here, right? That's my integral. I'm going very small, so this area is being squeezed. Its area will be always 0. So this will be 0, and if this is 0, its derivative is continuous. This is a discontinuity in the sense that this is equal to 1. So this cannot satisfy this equation. Same thing here, if this was continuous, this is a possible, or let's go here. Right? There's a possibility that it could be here. So right at this point, what is this? You again have this term will be 0. It is possible that its derivative has a discontinuity, but if this derivative has a discontinuity, the second derivative will have a derivative of a delta function. We don't want that. So notice what is happening here. It's the derivative here will have a delta function. Right? If its derivative has a delta function, its second derivative will have a derivative of a delta function. But we know that its second derivative does not have a derivative of a delta function. So this is not possible. Right? You argue that. And again, there is a possibility that it's infinite. Again, that's not possible because you cannot get a delta function. So the only possibility is that the Green's function is continuous and the derivative of the Green's function is not continuous. One can get this using algebraic methods also, but I feel this is more instructive. Just argue and proceed. Somewhere else we can do the algebraic. Using that condition, so our boundary conditions are, our continuity conditions are that G at Z prime plus delta, Z prime minus delta is equal to 0. Right? That means G is continuous. So this is Z equal to. And its derivative at Z equal to Z prime plus delta is equal to minus 1. Sorry. There was a minus sign here. That's a minus 1 here. Pay close. Make sure you understand this, how this comes from this differential equation itself. This is not a physical requirement. It's not the physics requiring it. It's a differential equation requiring it. So in any system, this will be true. Any questions there? Right, from that point on, it will be just algebraic. Notice in your homework problem, this analysis remains the same. Right? This doesn't require where the boundary condition is, right? We are somewhere close to Z prime, and there are two plates around that. So these two boundary conditions will remain exactly the same. In your analysis, this is where things will change. Also remember that exponential terms, when you add or subtract, there are hyperbolic functions which can be used to represent that. Okay. So now we have two more conditions. We just have to find the solution in terms of that equation. Okay, so we already know G, so let's write derivative of G, so that's K per times A exponential of e raised to K perp Z plus e raised to minus K perp Z. When I take the derivative, K perp comes down from the exponential, and the second term changes sign because it's a minus becomes a plus. And this is minus K perp E. And this is for 0. Okay. Use the boundary condition. So G plus delta to minus delta equal to 0. First plus delta means Z prime plus delta, that's second piece, right? Or I have to first go here, G, right? So that's D of e raised to minus K perp, and then Z prime plus delta minus of A times exponential of plus K perp Z prime minus delta minus e raised to K perp Z prime minus delta. I can take the limit delta tends to 0 immediately, because inside the exponential k perp, like z prime is greater than 0, so this will always is small, delta is small, so it doesn't matter. Its derivative, similarly, plus del chat minus del chat is equal to 0. That's the difference between these two. Right? So that's minus k perp d, exponential of minus k perp z prime plus del chat, and minus minus k perp a, exponential k perp z prime minus del chat plus is equal to minus 1. Take the limit delta tends to 0, so this equations read d e raised to minus k perp z prime minus a k perp z prime minus 0. I'll find a and d, remember. I'll divide out by k perp and divide out by minus sign also, so that this looks very similar. K perp z prime. When I divide out by minus, so this becomes a plus a. That's equal to 1 over k perp. How to find d and a? So d is equal to, I'll use the determinant method. So this multiplied, so I can write this as a determinant, right? So in the denominator, I would say this is e raised to minus k perp c prime, e raised to minus k perp c prime. This is minus and that's a determinant, right? Determinant of that, that's how you will get it. One way of doing it. I mean, there are probably easier ways to do this. On the top, you just replace this column with 0 and 1 over k perp, 0 and 1 over k perp, and do the same thing with determinant. Probably in this case, multiplying and dividing by some factors might be easier. But let's see. So this is equal to 0 times this, that's gone, minus of that, so it is plus 1 over 2 k perp, 1 over k perp, and there is e raised to k perp b prime, e raised to minus k perp b prime. Denominator, the other hand, this is exponential and this is 1. This is plus exponential of minus 2k perp z prime. This multiplied by this. This multiplied by this is a minus of that, so this is plus 1 again. And that is minus of e raised to minus 2. The denominator actually has a cancellation. So this is just simply 1 over 2k. It's pretty much algebra here. That's d. A similarly is equal to, I just have to replace the column, right? E raised to minus k perp z prime, e raised to minus k perp z prime, 0, and 1 over k perp. And the denominator here is exactly the same, but we said the denominator is 2. So why do this calculation again? So it's just 2. So So this whole thing came out to be 2. So that's equal to 1 over 2k per e raised to minus k per z prime. So we now know a and d. So we just have to go back and put it in there and we get our Green's function solution. Z, z prime is equal to a is 1 over 2k per e raised to minus k per z prime, and put in this factors also, right? E raised to k per z minus e raised to minus k per z. This is for 0 less than z prime. There's one more solution. We're going to interpret this next. Why do we have this structure? And that d is 1 over 2k per e raised to k per z prime minus e raised to minus k per z prime and z 0 z. What is this? We could just rewrite this again. 1 over 2k per z prime is greater, so this is minus k per z prime minus z minus of 1 over 2k per exponential of minus k per z plus z prime 0. This is z minus z prime. And the second piece actually stays the same. In fact, this whole thing can be written as when z is less than z prime is greater than z, that's this. And when z is greater than z prime, it flips kind of. So this can be written as in a single row, single expression is e raised to minus k per z minus z prime, the magnitude of that. And in fact, this also can be, it doesn't matter too much in this case because anyway, they are always greater, but one can say, you can think of this as magnitude of z plus magnitude of z prime, single. And we are going to interpret later, or actually today, that this is a 1 point charge, which is at plus a, and this is another point charge with a minus charge. Okay, so how do we go to our what's the connection between G and phi? If you notice, if you look at the two differential equations for phi, so comparing equations for phi of k per z and g of z comma z prime, we know that epsilon naught, right, of epsilon naught over q of phi k per z is actually equal to g of z comma z prime. It's just that we have to replace the z prime with a. So my electric potential modes, K per comma Z is equal to Q over epsilon naught, right? So Q over epsilon naught. So this is Q and this is a minus. So this is, let me write this as minus Q. And this is the source of this term here is the source of this image. Negative charge in there. So what's the total solution? So let me write down the total solution now. We will. So our total electric potential is 5R is equal to the electric potential is given in terms of modes, and you add up all the modes. Right? K per is a label for the mode. I a curve per dotted with R per pi of K per Z, where the electric potential mode equal to Q over epsilon naught but that seems to be mathematically closed, but how do we interpret this? Right? We need to have interpretation for what this means. Like what's the difference between this structure here and this structure? Here we want to interpret that. For that, we need to know what's the Green's function. Even though we know what's the Green's function for a point chart, basically electric potential for a point chart, what does it look like in this language? Like so the question we should ask is, so this is a complete solution now, but we need to interpret that. To interpret this, we ask a new question. What are, so for a point chart, single pointer, no conductor. In the absence of a conductor, this is in the presence of a conductor, right? Absence of a conductor. We know that the electric potential is, so let's call that phi naught, right? Phi naught. Green's function, that's what we call it. Phi of R is Q that's the simplest problem we know of a point charge with nothing around. That's your electric potential. But what are its Fourier modes? What is the phi naught K per? We ask what are the Fourier modes for phi naught? So you're naught k per z. What is that equal to? That's what we want to figure out, and we're going to show, like, it's not very obvious here, so we will show, right, in the next class that this is actually equal to q over epsilon naught times 1 over 2k per times e raised to minus k per z minus z prime, right, where z prime is the position of the charge, which is this piece. That's exactly this piece. But then what is that piece? That's not really the same. There's a slight difference in that, but we will try to interpret that. And that is where the image part comes in. This is actually, if you notice, if you are an observer here, and this is your positive charge, so this is actually, instead of looking at z, this is magnitude of z, and z prime is somewhere here, right? The magnitude of this distance is the same as this. So that's where that argument will come in. So a few more steps and we will see the complete. But the solution is the main thing. So it took some effort to get it, but it's good to get the mathematical structure so that you can use this for an unknown region also. And again, your homework, most of the analysis remains the same, except in this part, this will change because this time the C will not be 0 because you don't have this at infinity. Instead, it is at A. So there will be an A factors in here. It won't be C equal to 0. Write this in hyperbolic functions. That's my suggestion. Remember your hyperbolic functions. Use hyperbolic function instead of exponential. So sine hyperbolic of x is e raised to kx or e raised to x plus e raised to minus e raised to over 2. And cosine hyperbolic x is e raised to x plus e raised to minus x over 2. There is no i's in hyperbolic. So in fact, you can begin right from the beginning itself, right in the first piece itself, you can write sine hyperbolic, cosine hyperbolic. Right? That's also two solutions. So sine hyperbolic, cosine hyperbolic, and that will be simplicity. It'll be exactly like if you have done any quantum mechanics, it will be like solving for the electric potential in a, what is it called? In a well. Electric, not electric, particle in a box. That's what you say, in a one-dimensional box in quantum mechanics. Have you used that in any quantum mechanics course? No? Oh, both of you. Okay, so don't worry then. So this is the first time you're seeing this, and when you're doing quantum mechanics, you say, "Oh, I've seen this before." So you will see these equations coming again and again. It won't be called the Green's function as such, but Green's function is a method that is used. And, in quantum mechanics, usually you don't say use the word Green's function, but it's the same thing. Okay, that's all. Thank you.
So the K in Fourier space, it represents the modes, right?
That's
But is like the wave vector still an interpretation for K, or is that a different?
When it becomes a wave, it becomes the K. K becomes the wave vector. Right? This is wavelength, if you want. In this case, it's just wavelength. Right? Like if you have sine, if I want to write phi of t, right? Phi of, suppose phi of t, and t is, let's say, phi of x. Right? And if I write this in terms of sine and cosines, like sine mx plus cosine of mx. And if x is having a fixed domain, right, then this will be am and bm. So m is a label representing which sine function I'm talking about. Right? So this is sine of m, kind of which coefficient of which one. What is the interpretation of m there? M will be wavelength, correct? So that's one, or one will be, m will be 1 over wavelength, right? That's how you will interpret it. That's the same thing that's coming in here. It's just that it's a continuous variable. M is discrete here. Sine 1x, sine 2x, sine 3x. Here, this is all sine. So it's the wavelength if you want. Wavelength of what? There's an integral notice from minus infinity to plus infinity. Like what is wavelength of what here? Like this could be any function, right? Mathematical function. It has an interpretation of a wavelength there. But these are modes. I think that's why we say it's modes. If you want. Or electric field can be broken into sine functions, and each of those sine functions is variable. Does that make sense?
Yeah.
So when you talk about waves, this is electrostatics. When you go to a wave, like when you take off the condition of statics, then there is derivative with time, and that brings in the frequency. Then frequency and this wavelength get related. Then there is that interpretation of wave vector. At this point, we don't have it.
So since it's electrostatics, we could really have just the magnitude of K per, because
That's
there's no vector.
exactly. That is some vector. But there are two K-curves in the x and y directions in principle. You can say it's a vector, but it's not the interpretation of wave vector. It's just two directions, two wavelengths. That's it.
If it wasn't the same both ways.
And there is no frequency here at all. So that whole wave concept is not there. But yeah, it's the same.
Yeah, that helps.
On the homework, both homework problems, the same like process.
Yes. What's the first one? Remind me.
The first one I think is like what we were doing here. I don't remember if it's 1 or 2.
One of them is surely. Let me look it up. I think Curtis is left.